Hey, Charles, this is when we get to talk about reinforcement learning.
Hi, Michael. This is when I get to hear about reinforcement learning.
Wow, I'm glad we're on the same page. So,
Are we on the same page? Is this all of reinforcement learning, or is it just the reinforcement learning basics?
we're going to start with the basics.
Okay. I can't wait to hear what that is.
So, the first concept to try to understand when you're doing reinforcement learning is that a lot of it takes place as a conversation between an agent and an environment.
Okay, so like right now, you're the agent and I'm the environment?
Actually, I think I'm going to have you be the agent,
Okay.
and we'll just imagine some kind of, I don't know, like a video game environment.
That seems reasonable. By the way, have you noticed I've lost weight?
Oh, good job. How did you do that?
Well, I got drawn as a stick figure.
That's fair. So here we are, the agent and the environment, and the conversation basically talks about what is going back and forth between the agent and the environment. So the environment is going to reveal itself to you, to the agent, in the form of states, S. You then get to have some influence on the environment by taking actions, A, and then you also receive back, before the next state, some kind of reward for the most recent state action combination.
Okay, fair enough.
So this is the same kind of elements that we have in an MDP. But the important thing is that instead of just being given an MDP as some kind of a graph structure and then we get to compute on it, really the computation is happening inside the head of the agent, and the information about the environment is really only available through the course of this interaction. So does that make some sense?
It does make some sense, but I guess, how is that any different from the NDP?
Well, it's the same story as how a policy interacts with an MDP, right? Where this is playing the role of the MDP, and this is playing the role of the policy pi. But now, again, the computational aspect of the system here, the agent doesn't know the environment. It's not living inside the agent's head. Instead, the agent is just experiencing the environment by interacting with it. It could then, if it so chose, build some kind of a model of the environment in its head and then think about that. But what's in the agent's head and what's in the environment are two different things in this setup.
Okay, fair enough. I get that.
So maybe I can make this a little bit clearer. So let's actually put you in this environment. What do you say?
Okay, metaphorically?
No, let's just do it.
Sure.
So we've transported you into an MDP, or we didn't transport you into anything. We're giving you the ability to interact with an MDP. And here's the MDP. Now remember I said the MDP, or the environment, has states and actions. The states in this case are going to be visualized to you in terms of this sort of Mondrian looking picture in the middle of the screen.
Mondrian?
I'm going to go with that.
Okay.
And it's like colors and squares and things. And the actions are the numbers 1 through 6. And unlike in a regular video game, you don't know the rules. You don't really know how things work. You don't even know what it is you're trying to do. But what you can do is start playing and use that experience to start figuring out how things work.
Okay, so it's just like grad school.
Maybe. All right, so you have to now choose actions, and I'll enter them into the MDP, and we'll see what happens, and then you can see if you can win or not.
Okay.
Get my reward.
3. 3.
I did it. Just nothing changed.
5.
I did it. Nothing changed.
6. Huh. I'm back where I was.
That's true.
1.
Nothing changed.
2. 3.
That's a new state.
It is a new
3.
state. Oh, so I figured something out then.
Can you want to tell me what it is?
No, because I forgot what I did 2 steps back.
Okay.
I've decided that 3 means move to the right.
Okay.
And something moves down, but I can't remember what I said. I want to say it was 2, but I guess I could try that. 2. Yes. Now I need to figure out how to go back up again. 1.
Nothing happened.
4. 4. 4. 5.
Nothing happened.
6. So I think that's visually very attractive.
Thank you.
Oh, cool. So I think I know how to. I think my actions mostly move the orange square around, and now I just need to know what I'm trying to accomplish. How about 2? 2. 2. 2. 5.
Nothing happened.
6.
Nothing happened.
4. 4. 3. 3. 3. 2. 2. 3. 1,
Nothing happened.
4, 4, 4, 4.
All right, so you seem to have at least gotten a feel for the idea that there's 4 directional actions for the orange square.
Yeah.
In fact, maybe we should actually notate them just to make it a little bit easier to hold in your head.
Okay.
But you do notice that there are some actions that you haven't quite gotten to do anything yet.
Yeah. And now that I don't have to remember what they are. I mean, sure, 2, 3, 4, and 6 map exactly as you would expect them to down, right, up, and left. But I was having a hard time keeping them in my head. So let's try 6, 6, 2, 2, 6, 6, 4, 4. 1,
Nothing happened.
3, 6, 5. Oh, the little yellow circle thingy
Or green.
shrunk.
Green is good.
Okay, the green little circle thingy shrunk. 3. Oh, that's interesting. 2, 2, 3, 3, 3, 4, 4. I should do something now. 1.
Success!
Yes, I get it. I think I even understand what the game is.
Okay, well, let's show you the game again, and maybe you can explain it. All right, so here's another state. I just transported you randomly to another start state, and you claim that you understand how things work now. So can you explain?
Okay, I think I do. So the goal is to go get the little yellow circle, or the circle, which was yellow to begin with the last time. I don't know if that means anything. And
I think it was green last time.
was it? And you want to pick it up, which was I think 5. And when you do that, what I don't yet know is whether it will change color. But whatever color it is, when you pick it up, you want to take it to the square that matches that color.
Good.
And then put it down, which is action 1. Now, I should say, because I didn't say it before, that what I thought the point was the first time was just to get the square and the circle in the same place.
The square and the circle. Yeah, you did that, right? And then, but you didn't get any reward for that.
Right. So then I figured out maybe I didn't do anything. But at that time, I was also still trying to figure out what all the commands did.
Good.
I was doing a lot of exploring.
All right, so you learned a bit about the transition function. You learned a little bit about how actions change the state, and you also learned a little bit about what states are rewarding.
Yes.
And so now you think, even though things are a bit different, you think you could actually get kind of on a minimal path to a goal state now?
Sure. So from here, I would go 3, 3. Then I would go 4, 4. Then 5, which keeps it yellow. So then I need to go as quickly to yellow as I can. There's a lot of ways of doing that, but let's just do 2, 2, 6, 6, 6, 6, 2, 2. And then that doesn't work.
Is it possible you forgot something?
Oh, 1. I got to put it down.
Boom!
Done.
All right. So good. Excellent job. All right. So that was an MDP. In fact, you solved that a lot faster than any of the algorithms that we're going to be talking about, because you made use of all kinds of interesting background information about how you can, what navigation does and how it's consistent across states. But generally in the MDP model, in the reinforcement learning model, we don't necessarily assume that. It could very well be that what you're, in each state, the actions all do some other kind of crazy different thing. And you have to learn that mapping.
Right. So let me say 2 things. Actually, 3 things. One is, while I was trying to figure out what the actions were, I considered for a moment, even though I'd already figured out that 3 moved you right, I considered trying to go right a couple of times just to see if there was any randomness or stochasticity. But then I decided you wouldn't do that to me. You're too nice of a person. And so decided they were deterministic and didn't do that. But you point out that, yeah, I did it kind of fast because I had a lot of background knowledge. I'd really say that it was more about assumptions.
Okay.
And in fact, my first assumption was wrong.
Oh.
Right? That the goal was just to get in the same place as the circle, and that was the whole point.
That's true.
And then the last thing I'll say is that as long as I've been thinking about reinforcement learning, as long as I've been thinking about search algorithms and AI, and as long as I've been doing machine learning, I don't think I ever really appreciated just how incredibly frustrating it is when you don't actually know what the rules are and you're just trying to figure out what's going on. And I now am going to be much kinder to all of my search algorithms.
That's what I was hoping you'd get out of that. Thank you. Yeah. So sometimes it's really frustrating watching these algorithms do what they do, and in some cases just repeatedly bashing their heads against the wall. Which, for what it's worth, is something that you didn't do when you were moving around in the grid. You were purposely avoiding these dark black lines. Do you know why? Like, maybe those are actually reward lines. If you bump into them, you win.
Yeah, but every time I've ever played any game, they're walls.
Yeah, they look like walls, and in fact, they are in this case. So that again, that was an assumption that you brought to bear. But right. So when you watch a learning algorithm, a reinforcement learning algorithm, actually interacting with a grid like this, it doesn't have those biases necessarily, and so it can actually bash its head against this wall, and then maybe this wall for a while, and hey, this wall looks really fun. And so it's good that we have a little bit of empathy for the poor reinforcement learning agent that's trying to master this environment, given very complex and hard to parse apart representations for the actions and the states.
That's very good. Probably the only thing more frustrating than my trying to play this was all the people watching me trying to play this.
Oh, I think they loved it. For what it's worth, we can make this available if people want to play it on their home computers.
Yeah, but now they know the answer. Can you just randomly change what the actions are?
Let's say that I did that.
Okay. That was actually quite good. I'm glad you didn't let me know what it was beforehand.
Do you recognize it now?
Do I recognize what now?
It's
a taxi cab domain. I almost said that and then realized that would break the illusion.
So when I had Molly do this a long time ago, and I asked her at the end, what is exactly the task that this is supposed to be doing? She's like, well, you have to rescue the dog, and it just wants to go to its house.
Wow. That is...
Yeah. I thought that was kind of awesome.
We should try that with my daughter and see, assuming she could sit still long enough, and see what she would come up with.
The other thing is when you had it in this position and you really liked the kind of the symmetries of it and stuff, we actually did this in a mall in New Jersey where we had people come by and just see what they would do. We would give them the game and they would. And there was one woman who was a real estate agent who just could not get over the idea that the actual goal is to fix the feng shui. So if you look, there's a color in every corner. Except the blue is not quite in the corner. So she kept trying to move the blue into the corner. And when I told her that she should stop doing that, she just kept doing it because she was convinced that the task was one of feng shui.
I like that.
Yeah.
And that tells you everything you need to know about why our real estate market is the way it is.
and New Jersey. All right. So our goal is going to be to try to create learning algorithms that are not quite as smart as you were in that example, but trying to approximate that, getting as far along the Rock to Charles continuum as we possibly can.
Okay, we want algorithms that are Charles complete.
No, I think you're probably still going to beat the algorithms that we're going to talk about in this class, but someday. All right, so the important thing is that we have to figure out what it is that we are trying to learn. So in this case, what we're trying to learn is a behavior. We're trying to learn a way of interacting with the environment that obtains high reward. And it turns out that there's different ways to think about this depending on what kind of behavior you are looking for. So one classical kind of behavior that is very common in the AI literature is the notion of a plan. So a plan usually refers to a fixed sequence of actions. The kind of thing that says, okay, I see where I am now. This is the sequence of things I'm going to do. I'm going to go left, right, up, 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 down, pick up, left, down, 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 drop off, something like that. So that plan, once you've chosen the plan, you can just execute it. It's just that fixed sequence of actions. And this happens sometimes in real life. There's certain kinds of behaviors that we just have memorized as a sequence. But in fact, what's a problem with this? Why can't we, in general, just execute plans in order to satisfy the kind of goals that we're trying to satisfy?
Well, so I'll say two things. One is I was actually executing a plan once I figured out what was going on. Right?
Yeah, that's true. All right. So there's part of it is during learning, you don't know stuff, so you don't know what kind of plan to execute. For this slide, I'm talking about behavior structures for after learning. So during learning, all sorts of weird things have to happen. You have to try stuff out, you have to adapt. But once you've figured out what you want to do, you could try to represent it as a plan. But the problem with that, okay, so it is true. The environment that I showed you has a property that makes plans actually okay.
Yeah, it's deterministic for one thing. So that was the second thing I was going to say, which is that the plan worked because everything did as I expected it to do. It was deterministic.
Good. Good. And so in stochastic environments, you need to be at least a little bit of aware of your surroundings. You need to move around with your eyes open. And so one step in that direction is something called a conditional plan. So you can think of a conditional plan as actually being a kind of program where a plan is a fixed program where it just executes a sequence of statements. A conditional plan can have if statements in it. You can sort of see what's happening in your environment. I'm going to do this, this, and this, and this. And if I get to this point and such is true, then I'll go this way and start these actions. Otherwise, I'll try these things and these actions.
Right. So could one of your if things be if everything works out the way I expected, keep going. If it ever doesn't, then stop and try to figure out a new plan?
Usually that's not thought of that way. A conditional plan would be something where you have that sequence and then there's a branch point. We ask a question and we could, if everything's gone okay, continue the way we've been going. But if not, then a conditional plan has an else statement, right? It tells you what you should do in case that's not true or in case that something else is true.
Okay.
What you're talking about is something more akin to dynamic replanning, where the idea is exactly what you said. We're just going to continue along the plan, making predictions about what's supposed to happen next. If those predictions are violated, we just generate a new plan. So there's nothing in the plan that says, here's what I do in case things break. Instead, we wait for something to break and then we react to it.
Okay, fair enough. So that's just-in-time conditional planning.
Just-in-time planning, really, because the conditionals aren't in there.
Fair enough. I like that.
All right, now a stationary policy, which sometimes in the literature is referred to as a universal plan, is actually what we talked about in the context of MDPs. So mapping from states to actions. And this is a very powerful sort of thing because it can handle stochasticity really well. Every time you take a transition, you go back to your table, you go back to your policy to say, all right, here's the state that I ended up in. What's the right thing to do from here? It is kind of hard to convey these to people, though. Do you see why that might be?
Yeah. Well, so one way it might be is because I will claim that a stationary policy or universal plan is just a conditional plan where you have an if at every single possible state.
That's true, but it's actually a little bit more constrained than that, which is it's the same if at every possible state.
Right.
So no matter where you came from, no matter what you were in the middle of doing, once you discover where you are, that's going to determine what your next step's going to be.
Right, and that's a lot of if statements.
It's a lot of if statements. Yeah, and right. So if you try to convey it, you have to actually tell someone what all those if statements are. It's sort of like if I want to give you directions to my house, a plan might say, go left, go right, go left, go down until you get to Maple Street, make a right. A conditional plan might say something like, go to the highway. If you get there and it's crowded, then go these back roads. Otherwise, go on the highway. And a policy would say something like, for every location in my neighborhood, here's the direction that you should turn. And that's going to be very large. Right.
And in some ways not very useful.
Well, define useful, right? So it's very useful in the sense that it is very powerful and it can handle any kind of stochasticity. And there's always an optimal stationary policy for any MDP. Okay. So that's a really nice property. You never have to look beyond the stationary policies to find something that's optimal.
Okay, so then I take back what I said. It's not that it's not useful. It's that, in fact, it's very useful. It's that it's not very compact, or as you have up there, it's very large.
Very
so you have to say a lot.
Yeah. So that's exactly right. All right, but now for the learning algorithm, it could mean that it has to learn a lot. It has to discover what a reasonable thing to do is in every one of its possible states. So that could actually make the learning problem difficult. But anyway, I just wanted to at least raise this issue. We're going to be focused almost entirely on these stationary policies because they do allow for the possibility of expressing an optimal behavior.
Cool.
We're going to want our learning algorithms to return optimal policies.
Right.
But to do that, we're going to have to say what we mean by optimal. So I know we talked about this in the context of MDPs, but I thought it might be worth revisiting just to see that there's different choices we could make, and the choices that we make have implications about what it means to be optimal.
Okay.
So here's in particular what I want to get at. The notion that, let's say we have some particular policy that we're going to follow. By following that policy from some initial state, we're going to have a sequence of states, actions, and rewards. But there's actually multiple possible sequences of state, actions, and rewards that can happen because the domains are stochastic.
Right, right.
So let's say that we've got some particular policy that we want to evaluate, and it generates this kind of sequence of states with this probability, and this kind of sequence of states with this probability, and this kind of sequence of states with this probability. How do we turn all that possibilities into a single number so that we can say, oh, this policy is this good, has this value, and the other one is a smaller value, so I like this one better. All right? So here's the 4 steps that we need to do to take what was once a sequence of sequences or a set of sequences of states and turn them into a single number. So the first step is for each of the state transitions, we need to turn it into actual numbers, the immediate rewards.
Sure.
So in this case, maybe landing in a red state gets us minus 0.2 and landing in a green state gets us a positive 1. What is it in the definition of the MDP that allows us to translate between state transitions from some state via some action to some next state to actual values, actual numbers for that transition?
Oh, it's our reward function.
Exactly. That basically just gives us strings of numbers, right? So what was strings of states now becomes strings of numbers. And those are infinitely long, right? Because this process can continue in an unbounded way. If we're talking about the infinite horizon, we just leave it that way. But if we're talking about some kind of finite horizon, like, I don't know, say truncating it at 5 steps, we can actually take the sequence of numbers that results and cut it off after just 5 transitions.
Mm-hmm.
Now, we need to take that list of truncated numbers and for each of the sequences, turn it into a single number for that sequence. It's called the return for the sequence. So how do we do that? Yeah. Often what we'll do is actually add them according to some kind of discount factor.
Mm-hmm.
If R sub I is the reward that we got on step I of the sequence, we might want to actually sum up the discounted rewards.
Right, and my recollection is that that's a geometric sequence, so it allows us to do infinite sequences in finite time, or at least infinite numbers and make it a finite number, so to speak.
That's right. Yeah, no, and so that's a good point, actually, because we might be doing this finite or we might be doing this infinite. In general, we do it up to the length of the horizon.
Mm-hmm.
All right, and so let's just say for concreteness, you could imagine having a discount factor of 0.8, and that gives us a way of summing up the numbers that have been generated by these states and getting a single number for each sequence. And then finally, we have to take those multiple numbers, one number for each of the sequences, and turn it into a single number that summarizes across all of them.
I see. So you would just average them according to how likely the sequences are.
Good. So it's also taking the expectation. All right, and so I've annotated these sequences with their probability. So what you should be able to do at this point is actually, according to these parameters that I filled in, say what the value of this policy is, assuming that these are the 3 possible trajectories that could result. What is the single number that actually summarizes this, the output, the outcomes of this policy?
Right, and so that's when we talked about MDPs is long-term expected reward.
That's right, or value or utility.
Mm-hmm.
All right, so can you work out what it is for this case? We're going to make that a quiz.
Oh, okay. Let's pretend. Oh, wait, I've got one more thing. I think I know what the answer is, but just to force you to be, absolutely concrete. I know what happens when you hit a red circle. I know what happens when you hit a green circle. What happens when you hit a white circle?
Good question. They look like zeros. Let's just make them zeros. So they're not going to come into play except for the fact that they're 0.
I like it.
All right. So you should be able to reduce this entire sequence to a single number, and you can put the number in the box.
All right. Sounds good. Let's do it. Go.
Okay, Charles, how are we going to reduce this to a single number?
We're going to follow those steps that you have outlined. I don't know the answer, but I think I know how to get to the answer.
All right. Let's do it.
Okay. So, well, first off, are we doing finite or infinite here?
T equals 5, it says.
T equals 5. So we're definitely doing T equals. That's what I thought. Just wanted to be sure. Okay. Well, so all I have to do is actually turn everything that I see into turn the straight transitions into immediate reward. So I can do that. Would you mind writing some stuff for me?
Not at all.
Yeah, there you go. So let's do 1s over the greens and minus 0.2 over the reds. But actually, I don't really care about the one you just wrote down because it's more than t equals 5 away.
Ah, all right. Well, that's going to come up in the next step. Truncate according to horizon. So 1, 2, 3, 4, 5, cut. 1, 2, 3, 4, 5, cut. 1, 2, 3, 4, 5, cut. Now, I was a little bit sloppy with how I defined the 5. It could be that you actually put it one step deeper, but I was careful to pick a horizon length so that it wouldn't matter which way you interpreted it. This would just add zeros to it. It wouldn't change anything. So anyway, here we are cutting it at 5.
Okay, very smart, Michael. All right, cool. So now that we've done the truncating, I just need to summarize each of the sequences in turn. So I know that whatever I would get for the first value would be 0.8 to the 0 or to the 1? Where are we starting from?
That's another good question. So it looks, yeah, so that's going to actually change the answer depending on how people interpret that. I would say that what this is, to take this literally, that we're talking about the first reward, being R1, and then the next one being R2, R3, R4, R5, and the gamma corresponds to the index number here.
That doesn't seem right.
Yeah, but it is what it is.
Okay, seems like it should be 0, 1, 2, 3, 4.
Oh, I see. If you call the first one 0. Oh, I like that better. But probably for the quiz, we should accept either way.
Sure.
Or either way.
Or either way. Okay, so now that we know where each of the rewards is, that's pretty easy. Actually, I think that's going to work out pretty well for us. So then for the first sequence, I know it's going to be 1 times 0 plus 0.8 times 1. And actually, everything else is 0, so...
Yep. So this first sequence actually has a return of 0.8.
Right. So the second sequence is pretty similar. It's going to be 1 times 0 plus blah, blah, blah. So that's 8 to the third, or 0.8 to the third times 1, which is some number. Okay, so the return for the second sequence is 0.512. So for the third sequence, we're going to do the same thing. It's going to be 0.8 to the second power times 1.
First power.
To the first power. Thank you very much. 0.8 to the first power times 1, which is in fact 0.8, plus 0.8 to the fourth power times minus 0.2. All right, so we got 0.8, 0.512, and 0.71808. And so we just have to add those together, get an average, but a weighted average. So it's going to be 0.8 times 0.6 plus 0.512 times 0.1 plus 0.71808 times 0.3, which is obviously...
All right, so when you just work that out, then you get something that's very close to 0.75. So that's the summary of this particular outcomes of this particular policy according to these various parameters that we've chosen. So at this philosophical level, there's one last thing I want to talk about. We just talked about evaluating a policy, but remember, in the reinforcement learning setting, the policy is what gets output as a result of the learning process. So what if we want to actually evaluate the learner? How good is this learner? Can you think of some ways that we might be able to decide how good a learner is?
Sure. It's as good as its policy.
So that seems like a good idea, that a good learner is one that returns a good policy. Sure. What if we have two learners that return the same policy, say the optimal policy?
Oh, okay. Well, I can think of two responses to that. One is, who cares? They're both the same, and the only thing that matters is how good the policy is that you come up with. Or I could come up with another answer, which would be, I will take the one that does it more quickly.
Quickly in terms of what?
Let's say time.
I think that's what quickly means, yes. But like time of what? There's lots of different kinds of time that matter. So one in particular is computation time.
Yeah. Wall clock time.
And that seems like an important one, right? We want one that's going to be more efficient in terms of the computations that it does in the process of learning the policy. But there's another kind of time that actually matters a lot in the reinforcement learning setting. So I think it's worth mentioning.
Okay.
So the other kind of complexity that turns out to be really important in this learning setting is experience complexity. Do you have a sense of what that might mean?
How complex your experiences are?
I'm going to say no.
Oh, okay. Well, okay, get it. So computational complexity is sort of how much computational energy you have to put into it. So this would be how much experience you have to have in order to learn. So it's like the amount of data that you need.
Yeah, so if two different learners can learn the same optimal policy, but one only requires a couple interactions with the environment to do it, and the other one requires a billion, the one that has the lower experience complexity should be preferred, though of course there's trade-offs. I mean, if it to do that, it actually has to compute for 2 billion years, then that seems maybe not so good either. So there can be little trade-offs between how much time that the learner takes in terms of interactions with the environment and how much time that it takes in terms of the computations that it does between interactions.
So you know what this reminds me of? It reminds me of two things. It reminds me of Mimic, because that was the exact trade-off that we were making then.
Oh, yeah. Okay, sure.
And the other thing is it reminds me of the theory lecture that we did in the Intro to Machine Learning class when we talked about sample complexity.
Yes, that's good. That probably is a better name than experience complexity. Let's call it sample complexity. Yeah, because it really is about the data that's necessary to be able to achieve the learning ends.
All right.
All right, so this kind of sets the stage for what reinforcement learning is and how we compare different learners to each other and how we compare the outputs of those learners to each other. What we're going to dive into next is actual algorithms for doing this kind of learning.
Okay, that sounds cool. Can I ask you a question?
Sure.
So why aren't we talking about space?
Ooh. So space complexity. So that's a good question. In computer science, usually computation time and computation space are the two dimensions along which we evaluate algorithms. Here, I guess we could do that too. You could talk about the space that an algorithm uses, a learning algorithm uses, but it's generally not that interesting. Generally, we're not limited by the space complexity. We usually run into issues more quickly on the computational or the sample complexity side. So next time we're going to dive into algorithms and talk about temporal difference learning. So why don't we just sort of summarize the philosophical stuff that we talked about just now.
Okay.
So what have we learned?
So I think we learned a bunch of stuff, but we really learned three classes of things. We learned sort of what reinforcement learning is.
All right, that's one class of things.
Yeah, and as you wrote up there, we realized RL is about agents interacting with environments and getting rewards and sort of figuring out what the world is. And by the way, as a part of that, we learned just how frustrating it is to actually do reinforcement learning rather than just solving an MDP.
I agree with that.
Okay. The second thing we learned or we talked about was a description of what a policy is and the different ways you might go around solving these RL problems and evaluating them. What does it mean to have a good policy? Right. And then the third class of things that we learned was about evaluating learners. And we realized that there are lots of different ways to evaluate learners, just like there's lots of different ways to evaluate policies and plans. You can talk about truncating them or doing things that are infinite. We can talk about whether a learner is fast, whether a learner is efficient in a different sense, like with sample complexity, whether it actually returns good values. You can think about it just in terms of its output or how it got to its output.
Right, and so we're going to make some choices so that we have concrete algorithms that we can present and analyses that we can present. But it's worth keeping in mind that some of these things are kind of arbitrary. I mean, they're justified, but there's other things that would also be justified.
That seems fair in machine learning. All right, well, that all made sense to me, Michael. So I guess we'll continue this conversation next week.
Sounds good.
All right, have a good day.